Hello, welcome to this lesson in the chemistry tutor. We're going to work our last problem with stoichiometry, gas reaction stoichiometry problems here. And so the reaction that we want to discuss for this problem here is going to be the following. Magnesium as a solid plus 2HCl, hydrochloric acid, an aqueous solution, yields magnesium chloride as aqueous solution plus H2 gas. Now this is a balanced reaction already. You can verify that. One magnesium, two hydrogens, two chlorines, two chlorines. So everything's balanced. Now the question says, how many milligrams of magnesium must react with excess hydrochloric acid, HCl, to produce 28.50 milliliters of hydrogen gas, H2 gas, at 26 degrees Celsius and 758 torr. All right, so first thing you look at is you see you have a solid, aqueous, which means water solution, aqueous, and a gas. So we don't have two gases. There's no way we're going to be using volume ratios in this problem between two gases. We've done problems like that in the past. You understand the point with that. But we are going to have to use PV is equal to nRT here because notice it says how many milligrams of magnesium must react with excess hydrochloric acid. Excess just means you have so much hydrochloric acid that it's not the limiting factor here. You've got a whole bathtub of hydrochloric acid. You want to know how much magnesium needs to react with whatever, a whole bathtub of excess amount of hydrochloric acid to produce a fixed amount, 28.50 milliliters of hydrogen. The hydrogen's given to you in a volume, in terms of milliliters of volume. Okay, but we already know that we can't use volume ratios here. See, that's one way the students a lot of times will go off the rails here, is because this is given to you in terms of liters, 28.50 milliliters actually, and you want to figure out how much magnesium is produced. So if you start using volume ratios like 1 liter of this to 1 liter of magnesium, that makes no sense. You can't measure, well, you can measure a volume of magnesium as a solid, but using the mole ratios as volume ratios, it only works for gases. This is not a gas, so you can't do that. So they're kind of trying to trick you by giving you a volume of H2 gas to begin with. So what you need to start thinking about is, how can I get what I need from what I have? So 28.50 milliliters is the volume of hydrogen gas that I'm given. But I also know that this whole thing's happening at 26 degrees Celsius and 758 torr. So if I know the temperature and I know the pressure and I know the volume, 28.50 milliliters of hydrogen gas, and I certainly know the gas constant, R, PV is nRT, I should be able to figure out how many moles of hydrogen gas I'm basically producing. See, it tells me I'm producing 28.50 milliliters of hydrogen. I can use PV is equal to nRT to find out how many moles that is. Once I know how many moles this is, the one in front of this and the one in front of this, that's a mole ratio. So then I can use it to go back this direction and find out how many moles of magnesium, and then I can go from moles to grams always in chemistry, because you've been doing that forever. So we're going to use PV is equal to nRT first. And so to remind you of that, PV is equal to nRT. So the question is, what do we know and what do we need to know? Well, the pressure is given to us, 758 torr, right? The volume is 28.50 milliliters of hydrogen. All right, but we don't want it in milliliters. When we use PV as nRT, we always want liters, right? Remember the units of the gas constant: liters, atmospheres, moles, Kelvin, or liter, torr, moles, Kelvin. So you definitely want it in liters. So in order to move this guy and make it into liters, you move the decimal point 3 spots to the left. 1, 2, 3. So it'll be 0.02850 liters of H2. This is just how much hydrogen is produced at the end. Instead of milliliters, how many liters? Now the number of moles of that is what I'm trying to find. The gas constant, because the pressure is in torr, you want to use 62.364 liters torr mole Kelvin. Don't forget to use the proper gas constant. You got to use one that deals with torr, or you have to convert this to atmospheres first. Well, that's kind of a waste of time, so we'll just use that. And then the temperature. That was given to us as 26 degrees Celsius, but I know I don't want to use Celsius, so I just add 273.15 to it. And when you do this addition, you'll get 299.15 Kelvin. So you see what happens here. All the problem said is how many milligrams of magnesium need to react with excess hydrochloric acid to produce 28.50 milliliters of product hydrogen gas. But we know that all of this happens at a known pressure. This is how much volume of the product that we're getting. We know the gas constant, we know the temperature. So let's find out how many moles this actually corresponds to over here. So we'll plug it into PV is equal to nRT. So P is 758 torr. The volume is 0.0285. We'll just drop that last zero off there. So 0.0285. The number of moles is what I care about. And then R is 62.364 nRT, and T is 299.15, just like that. So on the left-hand side, I'll multiply these two guys, and I'll get 21.603. And on the right-hand side, I'll multiply these two guys, and I will get 18.656, 18.656 decimal 19, just like that, because that's an awfully large number down here. Now, in order to find the number of moles, which is N, I'll take this number, I'll divide by this one, moving it over there. So I'm going to get a really small number, 0.00116 moles of hydrogen gas. So this is how many moles. So if I were to rephrase the problem, now that I've done that calculation, I could rephrase it as follows. How many milligrams of magnesium must react with excess hydrochloric acid to produce 0.00116 moles of hydrogen gas as a product? So you see, the front work that we've done, the work that we've done so far has just simply been converting the volume they gave us in the problem to the number of moles. Now that I know how many moles I actually have, I can use the 1-to-1 mole ratio to go and figure out how many moles of magnesium I'm going to have, and then also to go to grams. So let us just do that right now. So we'll know 0.00116 moles of H2 gas. And I know I don't have to be totally explicit with you, but I will just to be sure. 1 mole of hydrogen to 1 mole of magnesium. So 1 mole of hydrogen to 1 mole of magnesium. So if I were to stop the calculation here, these cancel. If I do this here, you can see since it's 1/1, it's basically 0.00116 moles of magnesium. But the question didn't say how many moles of magnesium were required. It said how many milligrams. So how do I go from moles of magnesium to milligrams of magnesium, or to grams of magnesium? The way you do that is using the molar mass, right? So we know from the periodic table that 1 mole of magnesium, it's just a single atom. You just look it up in the periodic table and you'll see 24.305 grams of magnesium. So this cancels with this. So you don't even have to add anything together. It's not like it's 2 atoms or anything. You just look at the molar mass of magnesium and you'll see 24.305. So if we do this calculation, okay, and we go ahead and stop there. In fact, we don't really need to stop there. Since it wants milligrams anyway, let's just go ahead and finish the job here. We can say that 1 gram of magnesium is 1,000 milligrams of magnesium. Now this looks a little bit weird. Milligrams of magnesium. I know that looks a little bit weird, but that's how we're going to do it. So grams cancels with grams. So 0.00116 times 1 divided by 1 times 24.305 divided by 1 times 1,000. What you would get at the end of the day, 28.1, and that's milligrams of magnesium. I'll put an S here to remind you that this is milligrams of magnesium, which is a solid there, and that is the final answer. So these problems in reaction stoichiometry that involve gases, there's really 2 flavors. One of them is if you've got a gas reaction with lots of gases everywhere, then you can use those volume ratios to get where you're trying to go as far as the stoichiometry. The other class is more like what this one is. Whereas you're given a volume or something and you need to use PV is equal to nRT in order to make some progress to solve the problem. In this case, we needed to find the number of moles that was given to us in terms of the hydrogen, and then we use the molar ratio and go on through the molar mass to figure out how many milligrams of reactant that corresponds to. So if we take 28.1 milligrams of this magnesium, put it in a bathtub or some very large volume of hydrochloric acid. That's why it says with excess. It means you have so much of this stuff, it's not going to run out first. Okay, then it should produce exactly the amount of hydrogen that we specified in our problem statement. Okay, so make sure you can do this. Make sure you understand the concept of doing reaction stoichiometry that involve gases and using the ideal gas law, PV is equal to nRT. I think you have probably been able to ascertain through all the sections that we've been doing with the gas law, the ideal gas law, that it's incredibly useful in chemistry because you can use it for obviously calculating volumes and pressures and things, but you can also use them to solve much more complicated stoichiometry problems as well. Now I want you to follow me on to the next lesson. We're going to start to talk about the partial pressure of gases and learn about Dalton's law. It's really cool and interesting to learn about, and I'll take it step by step over there and learn about that. So make sure you understand this. Follow me on to the next lesson. We'll learn about partial pressures in a mixture of gases.